we have a representative from a lot of countries represented. And my third answer is the World Congress because of you, because of all of us here in Porto. I am told there are 610 people here this week from 45 countries. So I think, no doubt, a World Congress. Welcome to Porto, welcome to this event. I am confident that you are going to enjoy the next 3 days very much indeed. Before I pass on to Maurice, who is going to tell you more details about the program and what's waiting for you this week, I just wanted to highlight another special event that's taking place, or a couple of events that's taking place. FME Awards Prize is to recognize the work of colleagues. We have the FME Fellowship, we have the FME Lucas Award for highly influential paper. Normally we award one of these prizes per event. In this special occasion we have both events taking place. And these are basically very outstanding colleagues and pieces of work that are going to be presenting and talking about their work. So 2 extra invited talks, you could see them like that. So the Lucas Award this afternoon and the Fellowship Award tomorrow. Please don't miss that. I'm certain that we're going to have a good time. And I would also like to highlight a new Journal First track, a very prestigious track that we're bringing to FM in collaboration with formal aspects of computing and formal methods in systems design, where authors of papers, of outstanding papers published in these journals that have not been presented in a conference before, come here to tell us about their outstanding work. So, welcome to Porto. Enjoy the rest of the week. Thank you very much for attending. Thanks very much for being here, for contributing with your participation, submitting papers, and so on. It's your World Congress. It's you, really, who makes it the World Congress. So thank you very much, and thanks for our organizers. And I'll now pass on to Maurice to say a few words more about the event.
Thank you. So good morning also from, do you want to join? Well, as you want. So good morning also from me and Annabelle, and well, happy to see that the room is filling up for the invited talk that's coming up next. So just a few words on what was already anticipated by Anna about how much this is a World Congress. So this is the number of conferences, workshop, tutorials that we have in this week. And this is a very impressive number. And then I could have listed, of course, all the conferences, but they're quite good conferences around here. Some have started on Monday already, some starting today. So it's a very, very nice week. And then some highlights of the program. Also here, some anticipations already. So we have 3 keynotes from 3 different continents. Another sign of the World Congress. So these are from 9 to 10 each morning. Then we have 39 paper presentations in parallel sessions. And as already said by Anna, we have 3 Journal First presentations. So there will be 1 on Wednesday afternoon and 2 on Friday afternoon. I will provide some more details later. And well, we have the Lucas Award, as said, today after lunch. And we have the FMA Fellowship Award tomorrow after lunch. Then this afternoon there's an FME business meeting at 5 o'clock. And tomorrow at 3 o'clock there will be the announcement of FME 2021. So if you're curious about this, please come. And then of course there's the social event and dinner tomorrow at 3:30. And then we have an industry day. This is also a traditional event of FM. It will take place on Friday. There are 2 keynotes and 5 papers in the industry day. And it's from 9 in the morning until 4:30 in the afternoon. Unfortunately, in some sense, in parallel with the other technical talks of FM. Then some numbers, just to make it even more clear how much this is a World Congress. So we reached, well, there was not really a goal, but we ended up with 100 PC members. It was a goal to have them from many different countries, so there's 42 countries represented. And the reviewing task, we had 4 reviews per paper, so we also are very happy that 136 colleagues assisted the program committee members with all this reviewing work. There were 129 submissions in the end from 36 different countries. This was after we received 185 abstracts. So if you submitted an abstract and not the paper, please let us know why not, and we will try to raise the number. This was a big decline. It was somehow disappointing. So this is the total. Well, you can see the numbers. Lots of reviews, lots of comments. We had very intensive 2 weeks of discussion on all papers. And this was not an easy task. In the end, we ended up with 39 accepted papers, which are 37 research papers, and there was a tool and short paper category, and we also accepted 2 of those. And this makes up for a 30% acceptance rate, and well, the accepted papers come from lots of different countries as well. So we are, first of all, thanking everyone involved, so reviewing, but also, of course, those that submitted for all their hard work, and we believe this has led to a very interesting program. And let me just highlight a few things of this program. So first of all, these are the 3 journal first track papers that you can go and listen to. So one will be this afternoon and the other 2 on Friday. So you can find them in the program. And then there will be a Best Paper Award, and actually, well, 2 Best Paper Awards, but I will not say more. This will be announced during the conference dinner, so tomorrow evening. And then some authors of some selected papers will be invited after the conference. Also, this year we have 2 special issues planned, one in formal aspects of computing and one in formal aspects of systems design. And we are very happy also for the collaboration with these journals. Okay, so now I give the word to Annabelle, who will introduce our invited speaker.
Is there a Shriram in the room? Oh, you're there. I couldn't see you. Do you want to get your computer? Sorry.
You can go ahead and get started.
Right, okay. So our first speaker is Shriram Krishnamurthi, and he's a professor of computer science from Brown University. And Shriram is famous for a number of things, so I'll just list a couple of them.
Don't worry about
it. I have to do the intro. Okay. He's produced a number of influential systems, and he's written books on programming languages and programming. And today he's going to be telling us about the human in formal methods. So thank you very much, Shriram.
Thank you, Annabelle, and Maurice and everybody else for having me here. This is the relatively unaxiomatized part of formal methods, so let's dive in. So my background here, I'll use this. Is this on? Can you hear me? People in the back row, could you raise your hands? You can hear me. Okay, very good, thank you. That's maybe a little better, okay. Okay, so as background for this talk, for the past about 15 years, my students, my team, and I have built a bunch of different formal methods tools that we've applied in a variety of contexts, typically related to networking and security. And these tools, because we're building them for end users, we're building them for people who are not like the people in this room, have typically been built on top of model finding. So that's a phrase I'm going to use throughout this talk. What I mean is tools like Alloy, tools like SAT solvers, sometimes we use foundations like BDDs. The point is we want automation, but we still want a relatively rich language in which to write down our specifications. Okay? And for those of you who don't know about Alloy, by the way, there seems to be a workshop tomorrow called Formal System Design with Alloy and Electrum. I'm not part of it, but there's 4 really good people organizing it, so I expect it's going to be really awesome. So if you're interested, I would go check out this event and find out more about Alloy over there. Okay, so today's talk is about the human in formal methods. As you would expect from a title like that, I am primarily going to talk about tool users. But actually, I'm going to spend only about the first half of the talk talking about needs of users. The other half of the talk, I'm going to talk about another kind of human, which is students of formal methods. I see a few people snickering. For the purposes of this talk, let's define students to be humans, okay? And of course, the end goal is we would like those people to eventually become those people, right? That's a goal that a lot of people in this audience have. So let's see how to get there. So the first part is going to be about formal methods tools users. Let me start with a very concrete example. I'm going to put up an Alloy specification. You don't have to be able to read it. This talk does not require you to be able to read Alloy. But you might have a spec like this. This happens to be the syntax of Alloy. It's purposely designed to be sort of a bracey language, which I guess makes some people feel more comfortable. But what this is doing is it's setting up a basic gradebook system, okay? It's setting up a bunch of different roles, and it's expressing some relationships that connect them so that you understand what can be assigned to what in what sorts of ways, okay? You can also write predicates about the way the system evolves over time. For example, who's allowed to grade in this particular case. And finally, you of course want to write down some sort of property. So a property in this case, what this thing in Alloy syntax is saying is basically nobody can grade their own work, right? Very simple conflict of interest policy. So this is not meant to be a sophisticated example. It's not an advanced example. It's basically something you would do in the first week or two of your class just to get people warmed up, okay? So the question you want to ask Alloy or some other model finder is, can anybody grade their own homework? That's the thing you want to make sure cannot happen. And what happens when you use an automated tool like this is, in this case, the property is, you've all read it, of course, you've all paid attention, so you know exactly what the answer is. It's not true. Now, I don't expect that anybody actually followed that example, but I'm going to tell you it's not true, and what a model finder is going to do is it's going to give us a concrete counterexample. So a concrete counterexample might look like this. And you can tell that it's obviously quite subtle that this property is not true. There seem to be lots of different people involved, lots of different classes involved, and you'd have to spend a fair bit of time trying to understand all these relationships and trying to figure out where the spec failed, right? It's perhaps not immediately obvious to you how this counterexample is sort of what the key insight is in this counterexample. But if you happen to be trained in formal methods like we are, you'd stare at this for a moment and say, wait a minute, those look like two Skolem constants over there, and then there's a Skolem hull, and so what this is basically saying is actually just that. It turns out there's a very trivial counterexample because of the way this this system happens to be set up, right? I purposely gave you a very simple system description. There's a very simple counterexample, but the problem is that all you know that you're getting out of a tool like a SAT solver, SMT solver, Alloy, all you know is that you're going to get something that is a satisfying instance. You're going to get a model, and that's all you know. Which model you get, how that model shows up, what properties that model has beyond being a satisfying instance, there's really no guarantees. Okay? Let me give you another example. This one is, I'm not going to show you the spec. It's much, much longer. Basically, you can imagine a coding up of a Java type system, right? And you want to ask for a configuration. So one of the nice things about model finders is you don't even need to have a formal property. Right? This is one of the reasons we use them for non-technical users, like network administrators. They don't always have formal properties, but you can use the model finder to say, show me some instances, help me understand the spec that I've written, and maybe I might see something that's surprising or unexpected about it. So you can just say, show me an instance, show me a configuration, and you might get something that looks like this, right? You might think, wow, that's fairly complicated to get like a simple variable. That's a pretty advanced type system that I seem to have defined. Or in fact, it could also give you this, which is all you need as a minimal example. Okay? So what is going on here? What's going on here, as I said, is the tools are basically exposing to you some underlying solver. And what output you get from that solver is entirely up in the air, because there is no stronger property that the solver is giving you other than that this is an instance of the specification that you wrote. Okay? And if you use these enough, you start to realize there are all sorts of subtle things that can have impact. For example, you might change your solver because some solver works better on some kinds of specifications. The set of outputs could completely change. You might change your spec a little bit, and these things tend to be sensitive to small changes in the syntax of the input. So there's a lot of sensitivity here, and from a user's point of view, an end user's point of view, this is a pretty unhappy situation to be in, right? You don't want to get like extremely large models when a simple model would suffice. You don't want to impose a bigger cognitive burden than necessary. So if you, it's 9 o'clock in the morning, you've all been partying late, so if you need a metaphor to think about what's going on, basically this is like, the Dirty Harry metaphor, right? Like, you feel lucky, punk, right? That's the model you're going to get. You have no idea what you're going to get. Okay, so we embarked on a line of work. We're not the only ones. I will give credit to a bunch of other people in the course of the next few slides on what we've been calling principled model finding. So principled model finding is let's impose a stronger semantics on the output than just the fact that it is a model. Okay? So as you can guess from what I've shown you so far, a very good example of this might be, let's give a minimal model. So this is a system called aluminum. Those of you who are, of British persuasion or, the last pink bits, I appreciate that this is misspelled. Unfortunately, 3 of my co-authors are American, and, you can't do anything with Americans. So you can spell it differently and pronounce it differently if you prefer. Okay, so aluminum or aluminium. And the essential idea here is, I'll explain it in 4 quick pictures. Okay, so when you give a solver a spec, it's going to come up with a bunch of models. Those are the black dots. Now, these models are not completely distinct. For different notions of equality, these models will end up in equivalence classes, right? So what a tool like Alloy specifically does is it doesn't give you all of them. It uses a fairly clever algorithm for eliminating isomorphs, and so it's just going to give you one representative element of each set, okay? So of these equivalence classes, you won't see things that are equivalent. Unfortunately, there's no stronger guarantee about which of the red dots you're going to get. Okay? You might get a very small red dot, you might get a very big red dot. You can also traverse, you can browse with any of these model finding tools. You can say, show me another model. But there's no guarantee about the relationship between the previous model you got and the next model that you get. You're just getting models, right? That's all the guarantee you get. So this is essentially what I'm calling the Dirty Harry traversal metaphor. So we realize that there's really 2 parts to showing these models. One part is, well, we'd like to show you minimal models first, right? Put the least amount of cognitive burden on you, but also give you the mechanism. As you can see, the title of the paper is Principled Exploration. Give you mechanisms for growing the examples that you see, to see bigger examples if you need to. If you think maybe the example you've seen is not informative enough, you can grow it. But also, if you want to see a next model, what you really would like is show me something that's really different from what I've seen right now, right? So what you can do is you can eliminate this entire cone of models by inclusion, and when you say next, what you're going to get is something completely different, right? Think of this, if you want, as the Monty Python metaphor, right? And now for something completely different. So this was the basic idea behind this aluminum system. We're not the only people who've been working on this sort of thing, as I mentioned. There's some other really nice work in this area by other people. In fact, some of it, Alcino Cunha, Nino Macedo, and Tiago Guimarães are right here in Porto. They may even be in the room. Any of you here? Maybe not? Okay. Oh, excellent. Okay, very nice work. Okay, so this is really good work. You should go check it out. In our case, this is not true only of our work, but what we did was we actually built this completely on top of Alloy, so it's essentially a plug-in replacement. If you use Alloy in a class, you can simply strip out Alloy, put this in. The UI is the same, the language is the same. You just put a new jar file in. It's even called the same jar name, so you just put it in and everything's good to go. Okay, so you should download this and try it out. No, you shouldn't. You shouldn't download random things from the internet just because somebody tells you to. You should ask some questions. I mean, there's lots of reasons you shouldn't download things from the internet, but you should really be asking, well, this is all very good, but does it work? Now, I mean, we know what work means, right? You open a FM paper, and there's lots of different notions of work. So maybe you say, like, does it have a tool? Yes, it does. There's a screenshot. Do you have theorems? Well, why, yes, we do. We've got theorems as well. Do you have any performance numbers? Well, absolutely. We've got tables and stuff in the paper, just the kind of stuff, the usual evidence that we present at a conference paper. Okay? But we know that's not what work really means, right? What work here means is, does it actually make the user's life better? That was what we set out to do. So we did a bunch of informal studies and then started to do more formal studies. Let me present to you the outcome from one of these formal studies. So the scenario here is we're going to give people a model of reference counting memory management. We all know the problem with reference counting, which is that the algorithm can't handle cycles. So what we asked the study participants to do is to write a predicate that characterizes the situations in which this algorithm does not work. Basically, they were looking at soundness and completeness of this garbage collection method, and they had to write a predicate that says, here's where it doesn't work. So formally, it would look something like this. In fact, it looked exactly like this. So you're saying in every state for every heap cell, M is not in M hat, and what that hat means is that's Alloy's notation for transitive closure. Okay? So in 0 or more steps, if you start from M, you can't get back to M. Make sense? All clear? You can all write this in your sleep. Okay? So we did this particular study that I'm going to report on. We did with upper-level computer science students who were already experienced at Alloy, so we took care of some of the variables that could affect things. And we also, for reasons I'll explain in a moment, gave them aluminum, and we gave them another version of aluminum that maximizes, gives the biggest possible model. Now, that should scare you a little bit when I say biggest, but that's okay. It's well-defined in this case because we're working in a finite model situation. Right? So we're bounding the size of the models. Either we have some theorem that gives us a completeness bound, or we're artificially bounding the size, so the maximal model is a well-defined thing. Okay? So we give them either a minimal model or a maximal model. So for example, the minimal model might look like this, and the maximal model might look like that. So the idea here is we wanted to set off a little competition. We wanted to do this over multiple rounds. So we would first test the minimal versus maximal. And our hypothesis, which I would assume many of you would share, maximal is obviously a bad idea because the models are way too large and overwhelming and nobody's going to be able to read them. Minimal is probably going to do very well in some situations, but then there are going to be some situations where it doesn't work so well. And so the idea was we wanted to triangulate and see if we could somehow characterize, come up with an understanding of what kinds of models to present that would be really good for users. Oftentimes it would be minimal, sometimes it would be something bigger than minimal, and let's try to understand under which circumstances what kinds of models work. Does that make sense? Right? So first thing is to rule out maximal models and confirm that minimal works decently, and then narrow down from there. All right? Good? Okay, so the first study we did, we had about 35, I'm leaving out a little bit of detail here, but we had 35 subjects in one case, 25 in the max case. So how did it fare? Actually, it was a complete and total disaster. So what we did was we gave people the choice of opting out after a certain period of time if they really didn't like the model finder they'd been given. And it turns out of 35 subjects, 28 of them refused to have anything to do with minimal models. Okay? It appeals to us mathematically. Minimality has like a good flavor to it, has a good feel to it, but people were really frustrated by this idea. In fact, what's interesting is maximal models didn't do great, but did a heck of a lot better than minimal models did. Okay? We also saw several people who wrote the following spec. This is very similar to what I wrote earlier, except there's critically a little hat, a little transitive closure missing, right? What this is basically doing is it's eliminating self loops, but it's not eliminating transitive loops, right, in the heap. In fact, so you might think, well, okay, at least these 7 people who remained did very well. No, they did not. Only 3 of them got it right. And in the max case, only 2 of them got it right. Now, why is this? Well, let's look at those models a little more closely, okay? Here is our minimal and here's our maximal model. What do you see? Anyone see self loops? Right? The minimal counterexample to why garbage collection does not work is a self loop in the heap. That is the minimal example. Now, so in retrospect, it's completely obvious that this is going to be very misleading, and if these are the models you show people, that's what they're going to think is the characteristic situation they have to catch. But what's even more surprising is in the maximal case also they fell for this problem. Why is that? Well, visually, that is the most salient thing. Also, in this heap, there is actually a non-trivial cycle. And if you can't see it, well, that's an interesting user interface comment. It turns out that between heap cell 1 and heap cell 2, there's actually a double-headed arrow, but because it's a double-headed arrow rather than 2 arrows, you literally don't even see. We actually pointed this out to students. They said, oh, yes, you're right. If I have a double-headed arrow, that is actually a cycle. But there's nothing in the visualization that makes that salient. So some of this is a comment about visualization, obviously, but really a lot of this is a comment about the nature of these models and the nature of these principles that we were trying to use about minimization, which is that minimization can actually be actively misleading. So getting back to this competition, well, we sort of had a root disease in this tree. We never really got to explore this question more on this particular path. Okay? We kind of gave up and said we really need to understand better what's going on. We spent a lot of time also interviewing participants and doing sort of the usual thing that you do in this sort of situation. And we realized what people really wanted was not minimal models, but they wanted some explanation for why things were in their model. That's what they really wanted to know. When I see a fact, when something shows up in the model, I want to know why it's there. So there's a really nice piece of work from FM in 2008 on unsat cores. This is by Amina and Daniel and Felix Chang. And we were inspired by this work and made a variant of this, where what we do is we provide a provenance for everything that's in the output. So you can ask, why is something there? You can also, to a limited extent, ask, why is something not there, and get some explanation. What's really going on here, by the way, I think is quite interesting, because we're working with a model finder, but if I give you a why explanation, that's actually a deductive step. Right? Deductive systems are really good at whys because you can get a sequence of explanations. And typical model finding is pretty bad at that because it just says, it's true because I did some internal algorithm. So what we're really trying to do here is we're trying to extract a deductive result from the model finder output and try to present that to the user. So this is something we built as a plugin replacement for Alloy. No, wait, you shouldn't fall for this again, right? Okay, so there is a tool, but more interestingly, does the tool work? We did a different study on this question, and it actually doesn't do too badly. This is a very preliminary study. You can see actually unsat cores do quite badly at helping people find bugs and fix bugs in their specs. Provenance does somewhat better, but this is really preliminary. I'm not ready to call this a success. It just says that this is an avenue worth exploring more. Okay? So I will, there's a lot of detail here about studies. If you've ever done a user study, you know that it's a much more complicated thing than I'm making it out to be. There's a lot more detail. It's explained in this paper. I didn't want to spend the whole talk going into all the minutiae, but there's one interesting thing that's in this paper, which is, I didn't tell you who the subjects were for the second study, the provenance study. We actually did this on Mechanical Turk. Now, Mechanical Turk, some of you are probably well aware of it, some of you maybe less so. Mechanical Turk is a website where you can upload tasks and people will just show up and do tasks for you. It's extremely popular in some AI communities, so for vision algorithms and NLP and so on. They use these sort of cheap employees, these cheap micro-task employees to come in and label things for you or complete sentences or answer simple questions. Some people, my team inclusive, have used this for usable security studies, but it's not at all obvious how to use Mechanical Turk for doing something like a formal method study, because you don't have Alloy experts or Z3 experts or Coq experts sitting around, well, I assume none of you are on Mechanical Turk, so, sitting around on Turk waiting for tasks every day. So it's a little bit non-trivial to try to use Turk for this purpose, and there's a lot of good general advice on how to use Turk. What this paper also does is gives you some very concrete advice about how to set up a formal method study on Turk. So if anybody in the audience who's interested in doing these kinds of studies and wants to be able to get access for rapid prototyping purposes to a large audience of people, I would encourage you to go look at this paper just for that, forgetting about the other details, just to understand how to use Turk. Okay? Okay, that is most of what I wanted to say in the first part of my talk. Actually, you know what? Let's do this. Let's take a break for a moment. Why don't you ask me questions? Questions, comments, criticisms, anything at all? Yes, Jeremy.
So you talked about minimal models. I can see why using minimal models for exploring a specification is a bad idea. I don't want to find minimal examples. I want to find typical examples. But still, minimal models should be good for finding counterexamples.
Yeah, so that's a really astute observation. So Jeremy's point is, in fact, we purposely set up the study to fail, to be honest. We picked an example that we were dubious would work well with minimality, and in some sense it confirmed what we expected, that it didn't work very well. Partly based on our own observation, having built the tool and used it in a class, we started to see some issues. I think this is actually a really interesting point, that is, that when you want to debug something, you really would like you want the minimum viable, like the minimal counterexample to something. So what it shows is there's a real difference to whether you're using the tool for exploration or for debugging. And for debugging, we still think it's the right thing, right? But the goal we had set our students was not to find a bug, but to characterize a situation. And in that case, it's a really bad idea. So it's a really, really astute point. Yes. Any other quick comments, questions? Okay. There's actually a question I was hoping somebody would ask, which is, maybe you're asking the wrong question. And let me explain what I mean by this. Let me give you a very concrete example that has nothing to do with Alloy or formal methods or any of this other stuff. Simple programming question, right? So imagine that I have a binary tree data definition. Okay? what's a good example of a binary tree? Is that a good example of a binary tree? Okay, let's do a quick vote, okay? You're going to hum if you can agree. So if you think yes, hum. If you think no, hum. Okay, you think that's, okay, well, how about that? Is that a good example? Yes? No? Okay, all right, we're getting a little better. How about that? Is that a good example? Okay, how many think no? Okay, there's still some disagreement. In fact, what's the correct answer? Well, why not all of them? Right? If a student came to your office and said, explain binary trees to me, you wouldn't draw just one of them, right? What happened is we got sucked in by the tools. The tools that put us in a mindset of thinking about a single example to present, because that's what the tools do. That's what a SAT solver does. That's what, Alloy does. That's what all these tools do. But in fact, it's not clear that a single example is ever the right thing, especially for the purposes of understanding. In fact, you wouldn't stop there, right? You would also show students something like this to make sure they understand it can be imbalanced. You would also show them something like this to make sure they understand it can be degenerate, right? Once you have this collection, now maybe you've explained something about what a binary tree is. Okay, so really what's going on is traditionally, these solvers have taken a model of, you've given a spec and maybe a property, I'll give you a model. Or maybe, depending on how it's set up, maybe a stream of models. But really what we want instead is we want a set of models and maybe a stream of a set of models. That's what we really want, okay? So this is, again, work that people are starting to do now. There's more work along these lines. This work on what are called ensembles, at least that's the term we've been using. And the thing that's interesting when you start thinking about ensembles is it creates a new technical challenge. Because when you have a single model, well, that's pretty clear. But when you have an ensemble, you don't want to show every possible model. That's not going to be very helpful. So really, now you have to define some notion of coverage, right? But what is a correct notion of coverage of a specification? It's a little different from a program because in a spec, by definition, anything that comes out covers the spec because it's an instance of the spec, right? So coverage becomes a little subtle, and so these different papers do some various different things that are all getting at this notion of providing an ensemble instead. And I want to call out one other piece of work that I think is really neat that's not along these lines. This one is actually particularly interesting because it doesn't provide an ensemble, but provides non-models, okay? What it does is it provides you nearly satisfying models. So it gives you things that are not instances of the spec, but are kind of close, just outside the space, so you can understand the negative space of the specification that you wrote, okay? So I think there's much more interesting work starting to happen now as we're trying to understand what works and what doesn't for people. And what the high-level takeaway for this part of the talk is, when we think about user interfaces, user experience, and you maybe have colleagues, if you work at a university, you have like HCI colleagues, right? You might have the sense that a lot of what they think about is, visual aspects and, things like what colors do I use and what alignment do I use? And those are all important, as I've given you an example. But there's so much more to do. And us as a community have spent a lot of time thinking about the semantics of the input, meaning what is a good language for writing models? What is a good language for writing properties? But we haven't spent a lot of time thinking about the semantics of output, and I claim that is also a non-trivial space and worth exploring. So sort of my takeaway here is I think there's a really interesting interplay here between formal methods and HCI, and a lot more interesting stuff can be done if we take this combination seriously. Right? And since we're in Porto, I feel like obliged to draw a picture of a bridge, right? Okay, good. All right, that's the end of the first part of my talk. And now I want to talk about the other kind of humans, which is students. I've been following formal methods education since about 1996. In fact, one of the first repositories for formal methods education at Indiana was created by my wife, Kathy Fizzler, so I've been really following this quite closely for a very long time. And, there's a lot of explanations for why formal methods is not more popular, right? And I'm sure you have your favorite explanation. A lot of the explanations often revolve around, look, it's very mathematical, right? Students like to code. They like to just get their hands dirty. They don't like all this formal mathematical stuff. It's just not very appealing, right? So, I think that's a really good conjecture. And what that would imply is that there's no possible way for a field that requires you to know things like this to ever succeed, right? That would be absolutely dismal, right? And if you wanted to make a popular tool, there's no earthly way you should call it, something like TensorFlow, what even is a tensor, am I right? Like, what's a tensor? Nobody knows what a tensor is. So clearly, maybe that's not the whole explanation. Maybe there's more to what's going on. What I want to do is I want to tease these two words apart a little bit, right? So we have formal and we have methods. And we know that the formal stuff is, the stuff that seems to induce tears, at least for some students. But methods, I mean, students love this stuff. Now, I understand. I'm seeing like Annabelle and Cliff, and I realize that you people are a little appalled because I have quietly equated methods with tools. And I know you're thinking, like, how did I ever associate with this person? Don't worry, I understand there is a distinction. In fact, in Carol's invited talk on Monday at the Formal Methods Education Workshop, he's very explicit about this distinction. He said, look, it's not enough of our students just to understand a tool, understand something in the context of a tool. They really have to understand the concept. And I think that's a very wise warning. But frankly, I wish that is the biggest problem we have. If that's our single biggest problem, that would be a very happy space, and that's a good thing to work on. So I'm going to blur that distinction a little bit, and given my own background and given my own way of liking to think about these questions, I want to ask the following question. What does it mean to build an IDE for teaching formal methods? Now, again, there was an FIDE workshop on Monday, lots of really interesting work over there. A lot of the IDEs there are really trying to aim at like hardcore users, industrial users, whether they're technical or not, industrial users, big specifications, hard problems, embedded, and all sorts of things. I want to ask a very different question. What can an IDE do that's designed to help people learn formal methods? And I'm going to give an answer that I think is going to be different from most of the things that were talked about that day. So to motivate this, let me try to draw on some of the literature we actually have in computing education. There's a lot we understand in computing education, not about formal methods, but about programming. And those are not the same, but I think they're related, and some of the things will carry over. So I'm going to draw this very technical graph for you, okay? Science. I'm going to map out lines of code against frustration, all right? And I'm going to draw on two papers. There's a lot of literature that's related to this, but I'll draw on two specific papers. One of them is this paper from ICER. ICER is the International Conference on Computing Education Research. And it says something that will shock you. It says, participants often began coding without fully understanding the problem. Who knew? We've never seen that before. Leaving them with knowledge gaps in the problem requirements. And then this has all sorts of like downstream consequences when students try to solve problems. Okay, here's another paper from ICER 2018. The most frequent issue was a failure to build a correct conceptual model of the problem. Now, let's understand for a moment why this is a problem. I mean, it's like, it's frustrating, whatnot. The students are not solving the right problem. But if you give a student a task to do, chances are there was something you wanted them to learn from that task. Right? You designed this problem so they understand. Maybe you wanted them to understand transitive closure. You wanted them to understand, say, loops in the heap or something like that. And if the student doesn't get the right conceptual model, they are solving the wrong problem. So sure, you can give them a 0 on the homework or 25% on the homework, but the more important problem is there was some learning goal you had in mind, and that learning objective has not been met by the work they did. That's the bigger problem, and that's a bad problem because that's the thing that then accumulates over the course of a semester, over the course of some learning period, and at the end, they don't actually learn the things we're trying to get them to learn. So this is actually a pretty bad problem and something that should worry us a lot. So what happens here, so now I'm back to my quote-unquote graph, right? When you give a student a problem, there's initially this period of great anxiety. You don't suffer from this. That's why you are all like, at FM, right? But a typical student actually suffers from this. They have this blank page they have to somehow fill in, and so they start writing code because it's reassuring, right? And so they reduce this anxiety, they reduce their frustration as they go along, and then of course, students being students, they keep writing more and more code, right? I like say, they're like 3D printers, right? They only additively manufacture, right? If it's not good enough, surely more code is the solution to the problem, right? And of course, eventually they get to the point where the program doesn't work, and then they come back to you and they're like, what do I do now? Okay, so I don't know what this looks like. I don't know of any research. When I say I don't know, I mean I don't know, not that there isn't. And if people here know of good research on this, please talk to me because I'm looking for it. I don't know of good research that talks about these issues for writing formal method specifications. But I have a conjecture that graph probably looks a little bit more like that. Okay? but I don't know. But certainly it's not going to look a whole lot better than this graph, that's for sure. Okay? So there seems to be a lot of challenges here to overcome to get students comfortable, capable, and to actually learn the things we want them to learn. And the question now for this talk is, what can an IDE do to help with this? Okay? So I'm going to answer this in two ways. The first way is to say, well, the first thing is kind of a Hippocratic principle, right? Don't make things any worse than they need to be. So how can an IDE make things worse? Well, you know, there's been there's some of the talks we've heard and some of the work I've seen sort of advocates, look, the way to get students really excited about formal methods is to bring all these great industrial tools into the classroom. Okay? No question, that's a good thing to do, right? If you can say, hey, look, this tool was built by Facebook, that's way more credible than this tool was built by, you know, Shriram or something. So no, absolutely. But I think we have to do this very carefully. So when we think about any curriculum, right, you take a textbook doesn't start off on day one with all of the content you need to know, right? There's usually some kind of carefully graduated progression as you work your way through the material. Right? There's a name for this. These are called learning progressions. And we want students to achieve some level of comfort or mastery with one thing before we move on to the next thing. Okay? And, you know, in formal methods, like in my class, for example, you know, it happens to look like this. We start by making sure they understand predicate calculus, understand basic quantifiers, then we move on from there to relational operators, transitive closure, and then we move on to second-order quantification, right? This is our learning progression. Yours may be completely different. That's fine. The point is we all have some kind of learning progression, right? But the problem is our tools don't reflect these. Our tools don't honor the curricular abstractions we've put in place. Instead, you get the whole thing, whether you like it or not. You make a typo, and all of a sudden you've ended up in some other space in the tool. You can either get like a completely baffling error message, or you get something that actually quote-unquote works, but you have no idea what you've just done, right? So what you really need is you need to be able to introduce these features gradually. You need error messages that grow with the student's need. Basically, what you want is at every point, you essentially want an epistemic closure of what you were doing at that point, okay? And, you know, here's an example from Alloy. You know, Alloy, at some point, if you make the wrong kind of input, you'll get an error like this. It says, analysis cannot be performed since it requires higher order quantification that could not be scolomized. Now, everybody in this room is like, oh yeah, that makes perfect sense. I can see why that is. That's because you know what all the words mean, all right? And I mean, forget higher order logics. I've done these studies on beginners and basic programming, and it's really appalling how bad it is if the error messages have vocabulary they don't understand. And you'd be surprised by how much they don't understand. Okay? This stuff is really intimidating to students, and error output is the worst thing, because when there's an error, that's a moment when a student thinks, oh my God, I've done something wrong. Right? It's a really negative moment for them, and then making them feel bad about what they do and don't know is not a very good thing at that moment. Now, we have some ideas about how to do this. We've done this in the programming setting, so Dr. Racket is a programming environment. You can pick the Racket language, but you can also pick a teaching language, and you can grow which teaching language you're in. And in fact, different textbooks have different learning progressions and come with different sets of teaching languages for students to use. So we have the technology for doing this for programming. We could do this for formal methods. So what I would encourage is, as you're bringing these tools into your classroom, think very hard about the kind of learning environment you're creating and the ways in which students might come away feeling more intimidated rather than comforted by the importation of tools. Okay? So that's the Hippocratic part, right? But I want to talk about something more positive, which is how can we reduce the frustration? How can an IDE actually support the learning goals that we have? So if we think for a moment about our tools, we already have several modes in which they're operating. So, you know, we have like a spec and we have some properties. Classic thing, of course, is you verify. You check whether one of them conforms to the other. But you can also work just with the properties. You can do things like vacuity checking. You can also work just with the spec. You may not even have a property. And as I said, model finders are really good at giving you concrete instances, even if there's no property to check. Okay? So we've already got these modes, and maybe if you add more inputs, like if you add examples, you can add some notion of testing, and that would also work really well, okay? That's fine, but that has nothing to do with education per se, right? You should do that in every setting. That's not really education specific. Instead, I find it's useful to ask the question, what is really distinguishing about an educational setting? And I claim there's something really, really distinguishing that is not typical. It certainly does not happen in industry. And it happens most of the time in education, which is the following. we have ground truth. Most of the time, not always, when you hand out an assignment, you already know the answer, right? So, well, I hope. I mean, sometimes we purposely hand out assignments for which there is no answer. That's perfectly fine, or open-ended questions. But most of the time, we're trying to take somebody who's not yet an expert and bring them up to our level of expertise. So for every one of these artifacts that the student produces, we already have some expert version of that artifact. So the question is, what can we do with this? Now, I know, of course, what you're thinking is, oh, great, I can use this for grading, right? Yes, you can, and you probably already have some of these for auto-grading or something like that. I want to think about something more positive than just punitive things. I want to think about how we can use these to aid learning. So I'll give you 3 concrete examples of this, okay? First one, let's talk about helping students fix their specifications, right? So let's imagine that we've given them some model of a graph, and we've asked them to construct a predicate that says something like this. Some vertex has out edges to all the other vertices, okay? So you want them to write something like this. In fact, in Alloy, it's quite nice because you literally put the words some and all in the right places, okay? But if your students are anything like mine, they struggle with quantifiers, right? Yes, this is a familiar experience. They get the quantifiers reversed. They don't entirely know what the quantifiers mean. They put them at the right long level. They don't understand how the nesting works. All of these are problems that students run into. Okay, what can we do to help them? Imagine the student came to your office and said, hey, I've written this. Am I good? Am I good to go? You have a whole range of options, right? I mean, you can refuse to answer them. That may be not the most friendly thing you could do. You could say, nope, it's not correct. All the way at the other end, you could say, here's the correct answer. You don't want to just say, no, it's not correct. You want to give them more response than that. You don't want to just say, here's the correct answer. That's not helping them in the slightest. So what could you do? Well, here's a concrete thing you could do. You could give them a concrete example of how their spec isn't correct, right? You could say, for example, here is an example that matches what you wrote that doesn't match the English language problem that I gave you. Or, here is an example that matches the English language problem that you have not yet caught. Your spec does not cover, right? So you can give them this concrete set of examples, positive and negative examples. You can decide in what order you want to present them, and basically give those as concrete counterexamples to their claim that they are done, right? Well, this is actually a problem we have a lot of experience with. So my team's been working for about 15 years on this idea of what is called change impact analysis or differential analysis, basically semantic differencing. We were doing this in a setting where what we were trying to do was to help non-expert people in the field, like network operators or security policy authors, to understand how their policies were changing under little deltas. How do you make incremental improvements? How do you fix bugs? Or how do you, if you refactor your policy, how do you know whether you broke something? But it's the exact same problem, and we can take all of the knowledge we have from there and apply it in this setting. Right? So apply differential analysis between the student specification and the true specification. Give them concrete examples as a way of guiding them towards getting it right. Okay? Second example, they have property statements and they get the properties wrong. And we've been doing some studies of this lately. We don't have anything published yet, but we're starting to get there, where we're trying to understand in what ways do students screw up getting properties right. And there are 2 sort of obvious things, which is under-specification and over-specification. But we're starting to see some more subtle and more narrow issues. For example, they often set up a proxy criterion that's not quite right. So, as a simple example, imagine you ask them to talk about sortedness of a list. They might use as a proxy the length of the input and output list being the same, but the length is not a sufficient proxy for the actual content of the list. Okay? So they set up incorrect proxies because they don't understand that the proxy is not a sufficient proxy. Or they have symmetries that they don't recognize. Again, if you think about this list, what's very curious to me is there's this blind spot I'm seeing in students where they think to check that all of the elements of the input are in the output, but they don't check that all the elements of the output were in the input. Right? There's kind of this weird directionality they have that they seem to assume. Maybe it comes from programming, where they think that things sort of flow in one direction. So if I check that direction, I don't have to check the other direction. Okay? So we're starting to see these blind spots in how people write properties. Again, how can we help them? Same idea. It's differential analysis of a slightly different form, where we can help them understand ways in which they're falling short. Third example, last one, is how do we help them with this problem understanding, right? You remember I told you about this issue where they don't even understand the problem, and if they don't understand the problem, they're certainly not going to get to the learning objectives. Well, this paper actually goes on to say something quite interesting. It says, furthermore, there are no measures between viewing the problem and submitting code to ensure that the student understands what they're being asked to do, right? And that's now an actionable problem. So in the programming case, we've been working on this through a system called Exemplar, where what students do is they write examples before they write their code, and we run the examples against good and bad implementations, and basically we've gamified the whole thing so that they have to pass a certain, basically what's going on is examples or tests are classifiers, right? They classify good implementations as good and bad implementations as bad. So essentially you can imagine using precision and recall as a way of explaining how good your classifier is. How well does it classify good things as good, and how well does it classify bad things as bad, right? So that's the idea that we're using over there, and that's what we do in the programming context for checking understanding. Now we're porting those same idea, and it's worked out really, really well in the programming setting. So now we're starting to apply this in the formal methods case. So here's a prototype tool that we've built. So there's a spec where they have to talk about, they have to define undirected trees. But first they write down concrete examples. So what we've done is we have crafted over and under specifications. And what they do is they produce examples that are meant to catch all of these over and under specifications. So they can drag and drop and define this little example. And then they indicate whether it's a positive example or a negative example. They can say this is meant to be an undirected tree, or this is not an undirected tree. And depending on which one they pick, basically the classifier kicks in, and they get feedback telling them how well they did, whether they got it right or whether they got it wrong, and which cases they caught and what cases are still left to catch. Okay? And you can tweak the amount of feedback you give them, what kind of feedback you give them. These are all reasonable things to experiment with. Okay? So what I've shown you is once we add ground truth, there's lots of different and interesting modes we can build that will help students get better at writing formal methods. And even better, if we embed this in the IDE and give it to them, now it's sitting with them and they can use it all the time. They don't have to come for TA hours. They don't have to post online for help. We can give them concrete feedback even as they're doing this work. And so they have this continuous TA model, if you will. Okay? There's even more things we could be talking about. So in addition to this, there's also the question of writing proofs, right? The student could write proofs, we can have proofs, and every one of these things now interacts with all these other things in interesting ways. Okay? So what I want to end by saying is I think it would be nice if we could make more progress on this topic of formal methods education. There was a very nice workshop on Monday, lots of interesting papers, but I feel like we're still, some of the conversations we're having feel like they're a little old. We've had these conversations before, and it'd be good if we had more measurable progress in this area. And I'm not sure how much measurable progress we've had, partly because I don't know if we're doing enough to measure the progress. So taking all these artifacts, what we get is we get a richer experience for developing these things, right? We have multiple stages at which students write things. We have multiple representations, so these representations each has their own strengths and weaknesses. And finally, each of these has a different viewpoint, right? Each representation gives you some view of the world, and what we want is to combine these different viewpoints to arrive at some sort of improved student experience. We have a lot of experience doing this in the programming setting. We've got this book, How to Design Programs, that talks about how to do this sort of thing in a programming world. But there's really not, that I know of, a comparable sort of comprehensive view to doing this in the specification writing world and formal methods in general. Right? So what we want to do is we want to take this picture, like this is our little, the beautiful Duro Valley, if you will. It's very beautiful as a tourist monument, really not so beautiful as a student experience. And what we want to do is sort of level it out, right? Like, turn the Duro into New England or something like that. Okay? Not as beautiful, but maybe a better experience for students. Okay? So I want to end this talk by making a strong thesis statement. This is an unproven thesis. This is research work that I'm doing and hopefully others are doing, and I would like to hear from others who are, but also I think more of us should be doing. So this is my thesis here, right? With this multi-step process that involves a collection of these interrelated artifacts, we can bring a much broader population of people, much broader population than we're currently successfully addressing. And this broader population can successfully learn to use formal methods. That's the thesis that I'm working towards. Very preliminary for us at this point. We're trying to import all this knowledge from programming education, but we know that programs are not the same as specs. Programming is different from formal methods, so there are going to be differences, but I think there's still a lot to be learned from that literature as well. And this is what I hope we should all, like those of us who care about formal methods education, I hope this is the kind of thing we're all working towards. Okay? And that's the end of my talk, and now I would like